Hello. We are going to continue the second part of the normal distribution chapter. And last week, in the earlier part of this slide, we learned some basic properties of a continuous random variable. As you may remember, the continuous random variable is very much different from the discrete random variable, which we have considered so far. So first, one point has no probability for any continuous random variable. Thus, and there are uncountably many possible outcomes for a continuous random variable. So we cannot list all the possible outcomes and we cannot assign probabilities to each of the outcome. Therefore, assigning a probability to one point is always zero, so we have to change our approach to define the probability and describe the probability distribution. And I introduced two different approaches to define and characterize the probability distribution for a continuous random variable. One was the cumulative distribution function approach. The cumulative distribution function uh, is a function that if you enter a value, that it returns the probability that the random variable is smaller than the the input value. So as you change the input, the probability will change. And we also learned that you can calculate any probability using the CDF. And the second approach to the probability distribution of a continuous random variable is the probability density method. So the probability density is a curve. Usually we use the probability density function to for graphical illustration, graphical presentation of the probability distribution, and for the interpretation of the probability as a kind of area. We learned that the area below the curve, probability density curve, is the probability. And then, so these are some new features of continuous random variables. And the most popular continuous random variable is the normal distribution. It's not only popular, the most popular continuous random variable, but also it's the most popular distribution in statistics, not only in statistics, but also in any science. So we are learning really, really important chapter. And this chapter is very important. This is a very important preliminary setup and practice exercise for the later chapters because uh, from now on all the random variables will be approximated by a standard normal distribution, by a normal distribution. So you don't need to you if you know how to calculate the probability of a normal distribution, then you can handle most of the applications that I'm going to present in the later chapters. Anyhow, so the basis of uh, the normal distribution is the standard normal distribution. So normal distribution is parameterized by the mean and the variance, and the standard normal distribution refers to the normal distribution with these standard parameter values. The mean equals to 0 and the variance equals to 1, which implies the standard deviation is 1. So mean 0 and standard deviation 1. And we are going to use the standard normal distribution probabilities using Excel, Microsoft Excel. So we are going to compute the probabilities using Microsoft Excel, and later you will see that if you can compute the standard normal distribution, then you can handle any normal distribution. That's that is the conclusion of this chapter. The final goal of this chapter is to learn that you only need the standard normal distribution. That's what you're going to see. So getting used to the method, and getting used to the computation of standard normal probabilities is important and will help you in the later chapters. So let's see. I believe you have watched the videos about about the demonstration of Excel methods, and let's review what we are doing uh, in there. So suppose that our approach is using the CDF. The Excel, Microsoft Excel knows the CDF of the standard normal distribution. So by the definition, the CDF F, uppercase F, is the CDF of a standard normal distribution Z, random variable Z, which means F of A equals to the probability that Z is smaller than or equal to A. So this is the general definition. And what Excel does is, if you input A, then it will give you back, it will return the probability that corresponds to A. So you input A, then you are going to get this probability. So you can just put any number, and you can make it arbitrarily, uh, like you can do any like at any point. But in this in the Excel video, I have done these three numbers, but it can be automatically applicable to other points, other values. So I don't worry too much about working on other values. But remember, one thing that many students are confused is the direction of the inequality. Remember, cumulative distribution function, it's cumulative distribution function. So it accumulates the probability from the smallest possible value up to A, right? From the smallest possible value up to a point A that you uh, fix. So direction is like this. The random variable is smaller than the value. So this is what you have. Keep that in mind. Then a natural question is, how can we calculate probability of a different form? For example, probability greater than something. Probability greater than -1. This is different from the cumulative probability. It's not cumulative, it's greater than -1, -1 or larger. But still, we discussed how to calculate this probability. The key idea is we are going to use the complement rule. The probability that z is greater than -1 is the complement to the event that z is smaller than -1. So if you remember what I'm saying, try this question. It is easy. Of course, you can use Excel or a calculator, whatever program you want. Try this. And I'm going to turn to the next page in 3. 1, 2, 3. So this is what I said. Remember, probability greater than something is a complement to probability smaller than something. By the way, I am using weak inequalities in both probabilities because a continuous random variable has no probability at any point, at one point. So including one point or not does not change anything in terms of the probability. So, and it's my kind of writing habit to use weak inequality in general. But you may still use strict inequality here or here, does not matter. Anyhow, remember, this is true for a continuous random variable. So greater than something is 100% minus smaller than something. Then if you put minus 1, then probability smaller than minus 1 is the cumulative probability at minus 1. And this is what Excel tells you. Excel does not tell you this probability. It does not exist in Excel. Excel does not have this probability. To calculate this, or even on Excel, you have to calculate this first and then take 100% minus that. And in the end, the answer is 84.134%. So from the cumulative probability, you can calculate the probability greater than a point. That's what we learned in an earlier part of this slide. And if you, so it is 84.134 because the CDF at minus 1, it was 15.866. By the way, the answer, we calculated this and we got this. And it happened to be the same as f of 1. So let me explain why. So on the graph, if you use the PDF approach, probability density, using the probability density, you can visualize the probability as an area. The probability we are calculating is probability greater than minus 1, like this. And on the graph, on the bell curve, minus 1 is here, and we are looking for this area. But because a bell curve is symmetric about the mean, so this area, if you flip the left and right, or if you think about its mirror image, you have the same area in this way. So this area is the probability smaller than 1. So an alternative way to calculate probability greater than minus 1 is to calculate probability smaller than 1 instead of taking the complement. It's your choice. It does not matter what you use, but if you use the symmetry, you could do it this way. Then, anyhow, the answer is 84.134%, right? Okay, then now try this. So remember, these CDFs are probability smaller than the value. But you may be interested in probability in between 2 points. And we have also discussed how to handle probability between 2 points. Try this, and I'll be continuing in the next video. So please try it by yourself, and see you in the next video.